Hello and welcome to our final live textile build session. As always, you can join us on our Slack channel, or you can interact with us on our Google Q&A question and answer section, or you can post questions using the links at the top of the slide there. So thanks so much for joining us. Today is our final session. Here's the basic structure that we're going to cover. Essentially, this is our roundup and final discussion session. So we'll cover a few new topics, and then at the end of the session, we'll actually host a live Q&A session, hopefully over on Slack afterwards. I don't anticipate that this session will go particularly long, so we should have plenty of time if people have questions, want to tweak their final Dapp setup, or get some interaction time with the IPFS, or with the Textile team, rather. But to start with, we're going to cover a couple topics like just fine-tuning your IPFS setup, how to optimize your Dapp in the IPFS peer that's running in your Dapp. And then we'll actually go over a couple of alternative data storage sharing and decentralized web technologies, in particular focusing on a few projects with similar goals and implementations to IPFS and some of the concepts that we've talked about throughout this session. And then we'll kind of finish with a brief discussion of some of the limitations and benefits of decentralized apps and the decentralized web in general towards the end. So again, if you have any questions or want to interact with the team, please feel free to use our Slack channel. Otherwise, sit back and we'll have a good discussion today. So for most of our examples, including most of our browser-based decentralized app examples, we've just stuck with the default settings for our IPFS peers. And while the IPFS devs have come up with some very smart set of default options, certain configurations will actually be more useful in certain contexts than others. So it's actually important to figure out what will work best for your particular application. And why do we need to tweak this? Why can't they just get it right the first time? Well, because depending on how you will be interacting with the decentralized web, you may want to optimize for certain behaviors, and there really isn't a one-size-fits-all solution. For example, if you're hosting your personal or a commercial website on IPFS, you'll probably want to optimize for things like uptime, update speed, the findability of your site. So how easy is it to find it in the DHT, and other sort of considerations like that. Whereas if you're running a mobile peer that will be running on your, say, your client's phones, like our own Textile Photos app, then you'll probably want to optimize for things like memory consumption, battery or CPU usage. You'll probably want to minimize network requests, and maybe even avoid announcing, which blocks you actually have stored locally, or very specifically announcing it to a subset of the IPFS network. Certainly, you won't want to be running a public gateway on a phone, for instance, just for security reasons. Additionally, if you're running dApps in the browser, then you're probably going to want to optimize for browser functionality, things like load time, discoverability outside of the browser. You might want to bootstrap your peer with your own network of peers, because you're loading assets from IPFS. Maybe you want to customize which addresses your Dapp announces itself on, et cetera, et cetera. And we've actually toyed with a few of these things along the way when interacting with our own Dapp implementations as we've been building them up. So there's a lot of reasons why you might want to sort of optimize your different interactions. And sometimes you'll want to optimize a local peer, so one running on your local machine. And sometimes you'll want to optimize for a browser-based Dapp, so one running on, say, your client or your users' machines. So in order to enable some of these optimizations, you can actually just fine-tune your IPFS peers repo and daemon via its config options. Now, Textile has actually blogged about this before on our blog. So, and the reason being that the documentation for these options isn't great yet. IPFS and a lot of the tools around it, like much of the decentralized web tools, are still a work in progress, and things are changing constantly. So it's difficult to keep up with the documentation because it's changing constantly. But we've talked about this before, and so you can actually get more details on some of the topics I'm going to be talking about today at some of the blog links that I've posted at the end of the slides here. But basically, you can control how your peer does things like is addressed by other peers, what peers it connects to by default, how it stores and represents data, how it discovers other peers, et cetera, et cetera. And essentially, the format for the config file, you might have guessed, as things tend to be these days, is just a simple JSON structure with keys for different features, like what addresses your peer announces on, where your API is running from, what Bootstrap peers to connect to, how your data store is configured, how discovery is implemented, whether you reprovide content that you've pinned. You can tweak how the gateway interacts. It will store your peer's identity, which you actually don't have much control over, and how you interact with the larger IPFS swarm. Again, since we blogged about this before, we'll focus today mostly on configuration options that are relevant to decentralized apps, and then supporting those apps. So things that you might want to tweak in the browser, and things you might want to tweak on, say, server-side nodes to support browser-based apps. But again, there's a link at the end of the blog post to some of these link at the end of these slides to some of these blog posts that you can refer to for later. So first things first, you can control the addresses that your peer interacts on. And so you can start by tweaking these things pretty easily. There are three main options here, and you can control each of them by specifying a multi-address. And hopefully you remember those from some of our previous sessions. Basically, it describes the location of your particular peer, or in this case, the location of where your gateway will be running, including the port and protocol and all that stuff. And we've also actually talked about these configuration options in reference to the IPFS companion browser extension that we installed before, where you actually have to specify at which address to access your local peer. And again, we actually use the default, so you didn't really need to tweak anything here, but in fact, it is looking at the particular swarm and API and gateway addresses to know how to interact with your local peer. So, what do these controls actually mean? Well, your swarm addresses control which addresses your local daemon will listen to, or listen on for connections to other peers. And in fact, we actually modified this in our chat Dapp from last session to help our peers find each other when running in the browser. So you can specify at what address you actually want to listen on for connections. And if you specify a particular address and other peers are connecting, then you can specify, oh, this is the address I'm going to be listening on. If you want to connect to me, use this one. Conversely, your API address controls where your local daemon will serve its HTTP API from. And just in case you weren't aware, your IPFS peer is actually running a lightweight HTTP server for running IPFS commands, including on your local computer or server. So when you call, say, IPFS add, you're actually hitting this locally running server to process that command. So obviously, then you'd want to make sure that the address for the API is not accessible outside of your local host. Otherwise, bad actors could modify your peer or even pin files that you may not want pinned, or do nasty things that you probably don't want. So you want to be pretty careful about what address that runs on. By default, it runs on localhost and not an address, not a port accessible from outside of your machine. But in some cases, you may want to enable a slightly more public API address, and I'll talk about that in a little bit in the context of what you might want to do that. Similarly, you can control your gateway address as well, and that controls the address that your IPFS daemon will serve your local gateway interface from. So for browser peers, it's obviously not useful, and we don't have it enabled by default. But from a server peer, or like a peer running on your own local machine, if you want to be able to interact with IPFS-based files, say via a Web 2 site, then you'll probably want to access them via either the public gateway or your own private gateway, in which case you'd want to enable the gateway by specifying a gateway address. So for instance, when you access IPFS files over at ipfs.io/IPFS/the hash that you are looking for, which we've done quite a bit in this course, you're actually accessing a public gateway that's run by the IPFS community. It's actually a set of machines that are running public gateways. Textile, we actually have our own specialized public gateway that allows us to serve up encrypted files when the user has a specific access key. And I run my own personal public gateway just to support teaching and interacting with IPFS content online. But there's lots of reasons why you may or may not want to run a gateway. If you're running a local peer on a mobile phone, you don't probably want a gateway running, because that presents a security vulnerability. So there are other options under this particular setting, but these are the ones that are sort of most relevant to running or supporting dApps. Either running local server nodes with gateways so that your dApps can access assets through the gateway, or by modifying swarm addresses in your browser-based dApp in order to optimize finding other peers to connect with. Because a lot of what's going on when we're running dApps is interacting with other peers that are running the same dApp. Okay, and so speaking of APIs, there's actually a section of your config file that allows you to control how your API works. So again, if you're running a server, or a local machine, your daemon is running a lightweight HTTP server, and this responds to client requests. And that client, while normally is your local IPFS command line, you could also access it via curl or via another website or some web interface that you want to provide access to your server-side APIs. So you might want to update how your HTTP headers, header responses come from your API server. And so there's a HTTP headers sub-entry for the API item in your config that allows you to specify HTTP headers on responses from your API server. And why you might want to do that is if you want to have, say, additional access control methods, you want to maybe require authorization headers. Maybe you want to enable a public API, but you want to use JSON web tokens to control who has access to what API calls, for instance. So you want your users to access or to be able to pin or upload files to IPFS without actually having to run a local peer. Well, maybe they can go through your server peer, and you'd want to make sure that you can control how they actually access that. Because you don't want people just spamming your peer with garbage or illegal content or something. We've also actually controlled our API config option in these sessions, where we used it to allow cross-origin content. And we also enabled put, post, and get methods on our API when you're accessing it via the IPFS API node module that we were running in one of our dApps. That was actually the last 2 sessions that we were enabling that. And you may recall we did something like this to actually modify the config option. So there is a command line utility to modify your IPFS config the reason this is nice is it's possible to mess up your JSON config file if you forget a comma, or you forget to put a quotation mark where you should have, or you create an invalid option name or something like that. So if you want, you can actually access your config properties directly from the command line. And so that generally looks something like this, where you say IPFS config, and if you want to see your config options, then it's just IPFS config show. But if you want to modify them, then you might do IPFS config, and in this case, we're going to feed it in a JSON value, so we give it a JSON flag, and then you access the config option items hierarchically. So we want to modify the access control allow origin option of the HTTP headers sub option of the API key in our config. And in this case, we are going to allow cross-origin calls from localhost on 8000. The next one says that we're going to allow credentials, and we're going to set that option to true, an array of true. The last one is we're going to set our access control allowed methods to put, post, and get. So we feed it a JSON array there as well with quotes escaped. And so that's a nice way to interact with your config without actually having to worry about maybe messing things up. Alternatively, you can actually directly edit your config file, and then when you fire up your daemon, it will parse that and probably throw errors if anything got messed up. But anyway, there are lots of tweaks that can be made here, and for now, likely the only thing you're going to touch is the HTTP headers options here. And often, particularly for development, I'll set this up when I'm tweaking things. But you may want to lock things down when you actually deploy your peer publicly. All right, so on a separate note, that sort of brings us to our next option, which is our bootstrapping peers. So this is how you would control which peers your local daemon connects to when it fires up. And having a good set of bootstrap peers means, or provides the means rather, to bootstrap things like your distributed hash table, much more quickly learn who has what on the network, and maybe connect to particular content. Because of course, when you're interacting on IPFS, you're routing through your known connections. And you can't really find content unless you're able to interact with the DHT and find content. In fact, an isolated IPFS peer is almost useless because it would have no way to connect to any peers outside of its local network. It wouldn't know who has what content, how to access it, etc. So the default for the Bootstrap peers is actually a set of virtual private servers distributed around the world that's maintained by protocol labs in the IPFS community. But what if you wanted to run your own private IPFS network? That's a totally reasonable thing that you might want to do. You're running some sort of app, and you want all of your peers that are running your app to interact, but you don't necessarily want to interact with the broader IPFS DHT, for instance, because frankly, it's not important to your peers. Well, you can do that by running your own private IPFS network, and we'll talk about that in a little bit. Maybe you want to automatically include peers that are already under your control. So you've got some particular assets that are pinned on your local peers, and you want to ensure that any other peers in your network are automatically bootstrapped to connect to the peers that you have. You might want to tweak your Bootstrap peer list in order to speed discovery of those assets, for instance. There's lots of other reasons. For example, Textile, we use a custom set of IPFS peer nodes to ensure that our network is always up, it's connected and available for relaying photo updates and things like that to our connected mobile peers. And then once Filecoin is up and running, you probably want to have a set of known miners that you connect with when you fire up your peers. So there's lots of reasons why you might want to be able to control this. Right now, the default is a pretty good one, which is connecting to these global IPFS.io peers, but there are other options there as well. And so speaking of bootstrapping your distributed hash table, you can also control how your peer discovers other peers and how it interacts with the distributed hash table, or DHT. So by default on a local peer, multicast DNS peer discovery is enabled. And this is useful for peer discovery on local networks, which we've been using in some of our examples. So the chat example works best if you're interacting with multiple machines on the same local network. You maybe tried that. You maybe tried interacting with peers across a much wider area. The IPFS, or the Textile team here tested things out across North America. It works, but it's a bit slow. So DNS, multicast DNS, or MDNS, is useful for local peers. But if you're running, IPFS on machines with public IP addresses, where you actually have interaction to the outside world, then you probably can just disable this if you don't need to interact on your local on a local level. Related to this, you can control the interval option, which just controls the number of seconds to wait between discovery checks for MDNS. So for development, I often leave this on, and then for deploying, sometimes we'll turn it off because you just don't need it, and it's wasting resources. And that actually brings us to the content routing mode, which we can control. So this controls how your peer node actually finds and accesses content. And right now, IPFS uses a Kademlia, probably mispronouncing that, based distributed hash table. So to enable that, the option is just the DHT option. And as things progress and the IPFS community learns from cutting edge DHT research, that new options will become available. So by default, your peer will act as a DHT node. So it will add, route, and update information to the DHT. So it will store and serve small bits of data to the network, and it will answer queries that from other peers. So that's how IPFS distributes content. Things like IPNS records, content provider records, so who has what content, peer address records, etc. It usually doesn't take up that much memory, but constantly answering DHT queries can increase CPU usage. So particularly on light clients like mobile nodes, this can be a bit of a burden. So what you can do is you can actually set the routing mode to something like DHT client. And what happens is you don't serve requests to the IPFS network anymore, which saves you bandwidth. So you're essentially not participating in the DHT. And so your peer isn't a DHT node, but you can still query the DHT and figure out where content is located. You just won't be routing as many, or you won't be answering as many queries about routing and finding content. So for light clients and things like that, you may want to turn that down. Additionally, some people find, if they're running on AWS or some sort of cloud-based service, that their bill starts to skyrocket as they're getting all of these network queries. So you can tweak that by, participating less in the DHT, and that will reduce your bandwidth significantly. Of course, it's kind of important to have a good network of clients that are participating in the DHT, but there you go. Okay, so directly related to discovery, we actually have an entry for the reprovider. So this lets us control the time interval between rounds of reproviding local content to the routing system. So if you leave this off, every 12 hours, you basically reprovide. You say, I've got this stuff pinned, and if anyone wants it, they can get it from me. If you set that to 0, it essentially disables content reproviding. So this means that other nodes on the network, they won't know that you have a particular object or a particular block. So then they won't ask you for it, which again will reduce your network interactions. If you want to have this disabled, but you want to keep the network aware of what you have, so say you've got some important asset that you want to share, you need to manually announce your content. And we actually did have an example of that last session, where you can announce that you're providing something, IPFS provide. If you leave it enabled, which is generally a good idea if you actually want to increase your findability, then you might choose a particular strategy for deciding what should be announced. The default strategy is all, so you just say, you announce all of the things that you have locally, and that will announce all stored data. If you set it to pinned, it will only announce data that you've pinned locally. And if you set it to roots, then it will only announce directly pinned keys and root keys of recursive pins. So you can decide on how you want to do that. The pinned option is a good one if you want to interact over IPFS, but only actually announce things that you explicitly want to control. Okay, so finally we come to the swarm entry. And I say finally, there are a lot of other options in here to control how you tweak your peer, but I've kind of focused on just a subset of them. So options for configuring your swarm include things like something called an address filter, which is just an array of multi-addresses that you want to filter out or in for your peer when it interacts. So maybe you want to use this config setting, which is empty by default, to restrict peer connections to certain IP address ranges. So for example, you might want to exclude all IP4 peers and all IP6 link local peers to avoid connection issues that you might have. So NAT traversal techniques are sometimes required for certain network applications, like often peer-to-peer file sharing. But in some locations, like data centers, for instance, if you've got a big data center, a big cluster of peers, you don't need NAT discovery. So you can disable this and save a little bit of bandwidth. You can also disable bandwidth metrics. So when you're actually recording what kind of bandwidth usage you have, if you don't need that, you can turn that off, and you can probably expect a bit of a performance improvement, as well as a reduction in memory usage on your local machine. So if you don't need it, you can turn it off. Another two swarm config options that I almost always have enabled when I fire up a new IPFS peer is P2P circuit relay transport support. So to do this, you would set disable relay to false and hop relaying, or enable hop relay to true. So what these are is if you turn on relay hop, your node essentially acts as an intermediate or hop relay, it's sometimes called, peer in relay circuits for connected peers. So what this means is that essentially circuit relaying provides peers with the ability to indirectly connect with other peers who can't directly connect to each other, either because of NAT issues or because of protocol incompatibilities. So for instance, it's not that easy for browser-based, so JS IPFS peers, to connect to desktop-based or Go IPFS peers. But if your local Go peer has hop relay enabled, then it can actually it can act as an intermediary between essentially peers that are having trouble connecting. So it's a nice feature to have if you want to be able to relay information for browser-based dApps. And so a lot of what I do with Textile is building the dApps. So we've got a couple of peers that have this enabled to sort of support that relaying of information and connections and things. So other than these settings, you might also want to tweak your connection manager. So you can adjust the minimum number of peers you try to connect to, the maximum number of peers you try to connect to. The grace period that new connections are immune from being closed. In low power situations, you might want to increase grace period, but then reduce the maximum number of peers you interact with, things like that. And sort of speaking of which, it actually is possible. So there are actually these profiles that you can use when you fire up your daemon, which have a few of these config options kind of optimized for you already. So it's possible to start your IPFS daemon in low power mode, running from command line. And this actually also applies to running in the browser. But actually, some of these settings are already applied by default, which is nice. So, for instance, you can run your daemon using the low power profile, which is designed to reduce its overhead on the system. So, having said that, it can affect some functionality to some degree. So, interaction with the DHT is reduced. So the performance of content discovery and content fetching is reduced. And basically, when you run, say, your node in low power mode, what you're doing is behind the scenes, you're essentially setting your routing type to DHT client, which we talked about before. You're setting the reprovider interval to 0. So you're not telling people or telling other peers what content you have. And you're adjusting your minimal or low water mark. So minimum number of peers to connect to 20, and your maximum to 40, and your grace period to about a minute. And so this just essentially reduces network interactions and CPU usage. In this course, we've also played around with PubSub P2P communications already. And so we enabled the PubSub experiment. And that's pretty easy flag to enable. And we also enabled the namesys PubSub feature to more quickly propagate IPNS updates over the network via PubSub. And that's another simple flag that you can turn on. So these are all features I recommend experimenting with. There's a lot of these we enable by default. In particular, we pretty much always enable PubSub. Because our peers are running mobile devices, we're pretty serious about tweaking power consumption and memory usage. So we'll maybe not use the low power profile, but we'll tweak some of the config options manually to make sure that we're not burdening our own peers with network connections, things like that. And there are actually a lot of other experimental features that you might want to explore when sort of optimizing your IPFS peers. So enabling private networks is something that a lot of commercial-based users of IPFS are interested in doing, and that's something the IPFS community is very much for. So you can enable private networks with things like access control, and so that only your known peers can share content on IPFS or access your DHT. You can enable the newer IPFS file store option, which basically allows you to add local files to your IPFS repo without duplicating them on your system. So you can add these files, and you have to turn on the file store enabled config option. And then when you add content, you do IPFS add no copy. And what it'll do is instead basically just stores a reference to the data that's already on your local machine. So in case you didn't know, by default, when you add a file to IPFS, or obviously pin a remote file locally, it will actually make a copy of that file in your IPFS peers repo. So if you're not careful, or if you're adding like almost everything that's on your local hard drive, that hard drive will fill up pretty quickly because you're basically duplicating all of the data. So if you don't want to do that, then this is where this feature might be very handy to use. So for example, I actually run a small IPFS peer running on a local, just a little microcomputer with a hard drive attached to it. And I use that as a local backup for myself. And I'm just running a local private network in my house. And so I have the file store enabled so that when I'm backing up data onto that small hard drive, it's just sitting there one time rather than both in my repo and the actual original data, because I'm duplicating that data already in various places. So there's lots of different tweaks that you can do to use this. And I'll probably actually put up a blog post about my little backup storage solution at some point on the Textile blog if you're interested in that sort of thing. But actually, there's a link here in the slides to a master list of all the different experimental features, which gets updated as new experimental features come on board and existing experimental features get taken off as they become part of the core IPFS options. So, check back there and you can do a lot of fun things to tweak your peer setup. Okay, so I'm going to take a quick break and check to see if there are any questions on our Slack channel about any of the stuff that we've been talking about so far. And then we'll jump into our next topic, which is going to be talking about a few other projects in the distributed web space. So it looks like we're good for questions so far. And I think we can continue on. All right. So, all right. So we're going to change our focus a little bit here, both in terms of topic, but also in terms of sort of underlying technologies that we've been focused on. So far we've talked almost exclusively about IPFS and more general distributed web concepts, and we haven't really touched on other projects at all. This is mostly because Textile, we're building on top of IPFS, and so that's what we know and that's what we like, and we spent a lot of time deciding what distributed web platform we were going to focus on. But there are other players in the game, some of which are very complementary, some of which are competition for IPFS and Textile in general, but all of them share a common goal of a better, more open internet for everybody, almost ubiquitously. So it's an exciting time to be developing in this space, and there are a lot of really great developer communities to interact with, and I hope that you will do that as well. But let's take a quick look at some of these projects and see how others conceptualize the decentralized web. Now I'm going to focus specifically on decentralized web examples, so we're leaving out things like Ethereum, which already has tons and tons of courses devoted to it anyway, and more specific dApps like DTube and other sort of centralized clones. And we're going to instead focus on sort of complementary projects to IPFS. So anyway, let's get started, and you'll see what I'm talking about as we move through some of the different examples. So the first one here is I'm going to talk about is called ZeroNet, and their sort of tagline is open, free, and uncensorable websites using Bitcoin cryptography and the BitTorrent network. And so ZeroNet is, their primary focus seems to be on decentralized websites and avoiding censorship. So they use a public key infrastructure to publish private and so when you're publishing content, you use your private key, or sorry, your public key, and when you verify it, you use that public key to make sure that it was actually produced by that particular client to publish and verify site content. And then it actually uses your Bitcoin wallet to do this. So you kind of sign up for a Bitcoin wallet, you've got your public and private key, and we use those to actually publish and verify content. And then it uses essentially BitTorrent trackers for the actual data exchange, so for actually accessing sites. So each site on ZeroNet is essentially like a torrent file. And when you want to access the site, you essentially torrent that site and access the content from all sorts of peers distributed all over the place. You get little bits of data from each of them, and then you in the browser you'll visualize that content. Now, because censorship avoidance and privacy are important, they sort of support Tor to hide your IP address out of the box. And this is something that you can do with IPFS or pretty much any networking P2P solution out there. But ZeroNet kind of does that very purposefully. So the way ZeroNet works is each site has a JSON manifest, something called a content.json file. And in there, it has a bunch of references to other files. So when you visit a site, you will access that JSON manifest, and then you'll start pulling the referenced files from the BitTorrent swarm. So once you've visited a site, you're then seeding that site, right? Because you've accessed the content, and now so the more popular a site is, the more people that are connected to it, the more it will be seeded. So this is very similar, concept to a lot of decentralized web ideas. One of the nice things about ZeroNet is it supports dynamic updates through pushes. So once you're seeding a site, if the peer who is in charge of that site publishes changes, they get pushed to clients that are seeding it, and those pushes get sent out, and it propagates out into the rest of the network. There's a couple of really nice features, like you can do multi-user sites, so you can control who has access, who can add pages by adding new private keys for particular parts of the site. So that's a pretty powerful feature that lets you edit sites and pages collaboratively. And so a couple of nice features are, it's a completely alternative web distribution platform. ZeroNet is its own separate sort of network. They put a lot of focus on speed and user experience, and they don't claim to be competing with older projects or the sort of more traditional client-server model of websites. So this is just a sort of alternative decentralized network for sites. The real focus there is on site auditing, eliminating requirements for trust, and eliminating any type of discrimination. It is an open and transparent system, but it's not necessarily anonymous unless you're using Tor or something like that. So MadeSafe is another one, and their tagline is provide security and privacy for everyone on the planet. And so they do this with their decentralized and autonomous safe network. Obviously a pretty good name. And actually, quick side trivia, apparently MadeSafe was actually part of the inspiration for Pied Piper's decentralized internet in the HBO TV series Silicon Valley. So that's pretty cool, and you can say that the decentralized web has kind of hit mainstream in that sense. But that MadeSafe project is focused specifically on censorship, privacy, security, and control of your own personal data. And so these are all topics that we care a lot about at Textile as well. In this particular network, you essentially pay for adding content to the network, but not for browsing or accessing that. So it's free to browse, it's free to interact, and you pay for things using something called SafeCoin. And this SafeCoin market is a kind of an interesting one. It's a little bit different than you might expect from a coin-based market, and I'll talk about that in a second. But the theory, the MadeSafe sort of devs theory, is that it's a self-regulating market. So data and content is completely distributed across all peers in the network, and data storage is automatically decentralized. What this means is, if you're participating in the MadeSafe network, data is being stored on you sort of agree to seed some data. And that means that you don't have total control over what's on your system, as opposed to IPFS, where you only ever pin or seed what you want and what you've accessed. So that's a little bit of a difference there. And a couple of different options use this sort of fully decentralized and automatically decentralized data storage. So SafeCoin is the incentive mechanism for seeding content to the network. And it's kind of similar to the idea of Filecoin on IPFS. In MadeSafe, nodes are called vaults, and they're rewarded for storing and hosting data with SafeCoin. Everything is encrypted by default. Data is split into encrypted chunks, and it automatically is sharded across the network. You need to access things using the Safe browser, and that's your sort of secure gateway to accessing content on that network. And that Safe browser does things like it stores passwords, data, apps, etc. So you kind of need that browser that browser is your interface to the Safe network. The Safe coin is a very interesting thing. It's a digital cash, but it has no public ledger, and it can't be used outside of the Safe network. So it's not based on blockchain. Payments can actually be anonymous, and that's a big thing about MadeSafe is anonymity. And what essentially happens is it's not traded on any exchanges. It's just a coin that's traded entirely within the network in order to pay for access, uploads, and things like that. And then MadeSafe has MadeSafe coin, which you can use to buy SafeCoin and things like that. So they've got a whole sort of market-based ecosystem that's hopefully fully automated. So it's kind of a neat thing because they don't have a public ledger like a blockchain. Another really interesting project is this DAT / Hypercore / Beaker sort of ecosystem. So DAT itself is a nonprofit-backed data sharing protocol for applications of the future, is their tagline. So DAT is the protocol. It's developed by Code for Science and Society, which is a nonprofit organization with a bunch of funding from various private foundations. They're very public about where their funding comes from. And DAT is probably one of the closest competitions, say, to IPFS or competitors. And I use competitors pretty loosely because there are a lot of reasons why these both should exist and interact together. So DAT is based on a public key infrastructure where the files on DAT, unlike IPFS, which are content addressed on DAT, they're public key addressed. So you basically have these publicly addressed file archives, and you basically seed these archives, and people will access them, and they access these archives as websites or as data archives or whatever. So zip, public key addressed zip files that get automatically decompressed and accessed. One of the things that DAT focuses on is automatically tracking history, which IPFS doesn't do by default, but can do through tracking changes. Now, that's really nice feature because you can do versioning and things like this over DAT, but it means that it's difficult to share private keys between devices, because what you can end up with is these like sort of catastrophic splits in history if you sort of edit things from different using different keys. So that's a potential drawback, but there's a lot of nice features there as well. So Hypercore is actually the internal storage, content, and networking protocols of the DAT project. And so these feeds are sort of the core mechanisms, these Hypercore feeds. Essentially what they are is just binary append-only streams, and the contents are hashed, signed, and encrypted so that nobody can sort of spy in on access and content and things. And then Beaker, the Beaker browser, is a browser that supports DAT. And it's really designed to take advantage of a lot of the features that the DAT protocol provides. So the idea of sort of mutability of public key-based systems, the Beaker browser makes that really easy. It makes it really easy to do things like seeding, forking, editing, and publishing content. And so really, in the most explicit sense, the Beaker browser is your gateway to the DAT / Hypercore distributed web. And the team that's building it is great, and there's a very strong focus on usability. Anyway, in general, that project supports private data sharing, deduplication of content, and history of that content, which is very nice. And you can almost think of it like DAT is Git. It's the sort of protocols and the low-level interactions, and then Beaker is GitHub. Right? It's that higher-level interface that lets you do things like forking and editing and publishing. And that's the sort of way that I think about it, and I think it's a very nice ecosystem. If you're developing sites and things like that, I do highly recommend you check it out. Okay, and then Freenet is kind of one of our last ones I'm going to talk about. So Freenet sort of tagline is browse websites, post on forums, and publish files within Freenet with strong privacy protections. So Freenet is this P2P platform like all the other ones, but it's focused, or it's being used largely by activists and designed for people living in repressive regimes. It's the result of many academic papers, lots of developers interacting. It's been around for quite a while, and it's fairly well established. Its kind of main goal is that all interactions are anonymous. You can browse free sites freely without anyone being able to see where you're interacting with. You can chat, you can interact on forums without fear of your privacy being violated. Communications are routed through peers, very similar to like a Tor-style network. Okay. Now, again, data is stored across all peers in an encrypted format. So it's sharded across the whole network. So you may be storing things that you don't know about. Sort of one of the things that always makes you a little bit weary is, it's great that you can't easily discover what's in your data store, right? You don't really know what you're storing. and they're sort of on the website they say, and hopefully you can't be held accountable for what's stored there, and that can be a bit concerning, because you are storing other people's data potentially. It also has a few really nice features, like it has a web of trust or a high security mode. If you're in that mode, then you essentially only connect to known contacts. And so you have this sort of virtual private network that you can interact with and share content with without any possibility of spying on your connections. It was started by Mike Godwin of EFF. They're actively involved in court cases around censorship and censorship-resistant communication. Huge advocacy component to that project. It does sometimes come across as a little tinfoil hat-ish in terms of paranoia about privacy. So they'll strip out things like JavaScript and CSS and other unsafe assets to protect users. And it's a very, very sort of heavy-handed approach to privacy, but it's a very interesting project. And a lot of other projects have drawn inspiration from Freenet. And so there's a good explanation of it, quite long if you're interested in checking that out. And then the last one is Blockstack. So Blockstack is the easiest way to start developing decentralized blockchain apps. So Blockstack is essentially a fully decentralized standalone internet that tries to be essentially like it's got all the bells and whistles built into it. So it comes with a full stack of open source developer tools to build and essentially bootstrap decentralized apps, and even new protocols to build on top of it. It comes with its own decentralized DNS system that's stored on the Ethereum blockchain. It does require a specialized browser to interact with, and that browser stores things like your passwords and apps that you have enabled and things like that. On their website, they sort of compare Blockstack to, let's say, Firebase style stack. So it's got a stack of SDKs. It's got a browser. It's got a DNS or BNS system, decentralized storage, sort of one-stop shop for your decentralized interactions. It even has its own layer 2 blockchain. So layer 2 blockchain is a blockchain that operates basically on top of another blockchain for optimization reasons. And they have a big focus on data ownership, privacy, security, and freedom to interact across apps and things like that. So again, it's like a full-featured alternative decentralized internet. It's currently very developer-focused. So there's a lot of really nice developer tools trying to bootstrap apps in the Blockstack space. And they have some featured apps, which are pretty cool. I highly recommend you check them out. Because they provide nice things like ID, facilities for storing personal data, APIs, and a nice developer platform, etc. So they're really focused on that sort of application layer level, which maybe IPFS currently is less focused on. They're more focused on the lower level interactions. Okay, and then I won't dwell on Tor, but I do have it here as a special mention because so many of these projects actually enable or build on top of this concept of a Tor network. So I'll leave that up there for you to kind of take a look at. And we'll move on to some final thoughts. So we've got about 5 minutes left. So we'll talk about this, and then we'll shift over to Slack for live Q&A if anyone is interested in that. So just some final thoughts here. Just because you can decentralize maybe doesn't necessarily mean you need to. So, we've talked about the future of the web quite a bit in this series of tutorials. The future of web is unlikely to be completely decentralized anytime soon. Excitement around this whole concept of a fully decentralized web is increasing. But what we do see a little bit of is this trend of taking existing centralized services and just fully decentralizing them, primarily just because we can do that. But in some cases, these 100% decentralized versions don't necessarily provide enough additional value on top of the centralized version. There are very good social, technical, and implementation reasons for decentralizing. plus decentralized interactions, they come with a whole new set of, kind of very interesting problems that they can solve, right? So, it's kind of my opinion that focusing on the novelty and features that decentralization brings is better than just decentralizing existing centralized apps. So rather than shoehorning, these existing centralized features into decentralized space, it's probably a good idea to think about what do we get when we have no centralized authority? What do we get when identity is actually a lot harder to kind of conceptualize, is a lot harder to define? And think about things like, does your product need to be decentralized? Maybe not, unless you need it to operate in a fully trustless environment, immune to censorship, that you want your app to exist without you necessarily. And then on top of that, you have to think about, well, okay, how will you monetize that Dapp in the future, or right away? These types of things, because a lot of the time, once you develop and release a Dapp, it can exist and it will continue to exist as long as people interact with it. So, kind of monetizing that after the fact is a little bit harder unless you're going to develop a new and better version, that sort of thing. And then chances are you probably don't need a blockchain, but that's just a sort of running joke in the decentralized web community, is, chucking the word blockchain in your proposal for grants or for interacting with VCs is probably, might help you, but you probably don't need it. But we do gain a lot when we start to decentralize our applications. So, the product becomes essentially uncontrollable, uncensorable. So, some examples that people have used is, well, a decentralized Uber or Airbnb may be actually a really great idea because, in places where there's tends to be a whole lot of sort of heavy-handed control over transportation regulations, a decentralized version of that app can't be stopped. There's no centralized servers. You can't say, hey, Uber, stop doing this, because the app is distributed across all the people who are using it. So in these sorts of situations, it may be, a good example of how that might work. The other nice thing about decentralized applications is user motivations often become clearer, and ownership of that content sometimes becomes more explicit, because it's sort of built within the community, for the community, by the community. Motivations end up being a lot more explicit. So instead of using this app because it's free, now I'm using this app because it provides the features that I want, or because it keeps my interactions private, or so on and so forth. And there does tend to be a pretty clear focus on cryptography and security as the default on this decentralized web, which is something that's just really a good idea in general. Plus, from a developer's point of view, there's a very engaged developer community that I hope, now that you've interacted with us here through Textile Build, you'll start to interact there as well. And there are lots of examples where decentralized works really well. Databases and storage, perfect application. Compute time, that seems to be a really growing area where spreading out computation across worker nodes or worker peers looks like a very promising way to distribute access to compute resources. Obviously, currencies and exchanges are the sort of default when talking about these types of systems, but things like social networks are also an obvious one. Though things like network effects make this transition to decentralized a little bit harder, right? If you want to get noticed, you got to be on Instagram or Twitter, and some of the more decentralized social networking platforms are slow, to adopt. But that's pretty normal for any sort of change like that. But at the end of the day, here at Textile, we kind of want you to think about the user experience. So right now, it seems like in general, a sort of hybrid approach between centralized and decentralized provides a pretty good user experience. Textile is trying to develop those lower level tools to essentially make a fully decentralized app also a very nice user experience. So we're doing work around identity, encryption tools, building SDKs and UX and UI facilities for mobile. So it's early days for a lot of this stuff, and I think a lot of companies are going to start building on top of and leapfrogging on top of a lot of the work that's being done right now. So with that, I've got to have a little bit of a plug for our own stuff here. So don't forget to check out some of our projects. In particular, check out our GitHub, where you can see some of the actual Dapp development that Textile is doing. And we take this sort of idea pretty seriously. So hopefully, as you move along, interact with us. Don't be a stranger, and please reach out if you've got any questions. The Slack channel for this course will continue to exist in our public Slack space, so we can use that as a space to talk about Dapp development and that sort of thing. We'll continue to produce blogs and posts about interacting with IPFS and the distributed web in general, and we hope that you'll interact with that content as well. So just a quick wrap up here. What did we accomplish in our 5 sessions over the past couple of weeks? Well, we covered things like fundamentals, exploration of IPFS. We developed a prototype Dapp. We interacted and learned technical skills needed to interact with decentralized apps. And we even discussed some of the limitations and sort of other decentralized web technologies along the way. So hopefully you all ended up with something like this. And if you're struggling with any of the Dapp examples that we had throughout the course, please do reach out over on Slack, and we can help you get that stuff going. With that, that's pretty much all we're going to cover for today. Please do stay in touch. If you've got the slides here, these are links to various ways that you can interact with Textile and the Textile build team. You can hit us up on Slack, Twitter, Telegram, continue to follow our blog and GitHub, and you can send us emails as well. So I'm going to switch over to Slack, the Slack channel here, where you can join us for final Q&A, questions about the Dapp development and that sort of thing. So please feel free to join us there. Otherwise, I will sign off here with a few additional resources and links, and we will catch you on the decentralized web. So thanks again very much for interacting with us, and hopefully you've enjoyed this series. We will be sending out a sort of post-series survey to ask you about topics that you enjoyed, topics that you didn't enjoy. It will be fully anonymous, so please do be honest and let us know what worked and what didn't work, and we will do our best to produce some more useful content. Thanks very much.